All right, so this last video for the unit is on conservation of momentum and collisions. And we're going to start off by showing another little video clip.
You saw how a force applied during a time interval changes the momentum of a baseball. According to Newton's third law of motion, forces are the result of interactions between two objects. The force of a bat on a ball is accompanied by an equal and opposite force of the ball on the bat. Does the momentum of the bat therefore also change? Let's consider the collision of two balls. During the collision, each one briefly exerts a force on the other. Despite the differences in sizes and velocities of the balls, the forces that they exert on each other are equal and opposite, according to Newton's third law of motion. These forces are represented by the equation shown here. How do the impulses imparted by both balls compare? Because the time intervals over which the forces are exerted are the same, the impulses must be equal in magnitude but opposite in direction. How did the momenta of the balls change as a result of the collision? According to the impulse momentum theorem, the change in momentum is equal to the impulse. Let's compare the changes in the momenta of the two balls. Because the time interval over which the forces were exerted is the same, the impulses are equal in magnitude, but opposite in direction. Substituting impulses with the change in momentum for both balls, we arrive at the equation shown here. This equation states that the sum of the momenta of the balls is the same before and after the collision. That is, the momentum gained by one ball is equal to the momentum lost by the other. If the system is defined as the two balls, the momentum of the system is constant, and therefore momentum is conserved for the system.
So that's the conservation of momentum. That momentum is conserved even during a collision. Okay, let's go back to these two little pictures of the two objects making contact with each other. So if we look at that, so we're going to look at under which conditions is momentum of the system of the two balls conserved. Okay, so they don't gain any objects, so it's a closed system. Nothing is being added or taken away from it. And there's no net forces acting on any of the objects. There's the forces. There's one ball hitting on the other one, exerting a force on the other one. Okay. So if we move on, so no system on Earth can be absolutely isolated because there's always some interaction with the surroundings. Okay, and we can ignore them usually. All right. So systems can contain any number of objects, and the objects can stick together or come apart in a collision. We're going to look at the different types of collisions, but they always follow the law of conservation of momentum. That says the total momentum of the system doesn't change. Okay, and you're going to be able to make some connections, and we're going to do some math problems with these. So here are your types of collisions. You have what's called an elastic collision, where they hit and bounce off each other. I figure like two pool balls hit and bounce off. You have an inelastic collision, where they hit and they stick together. And then you have an explosion, where they start together and they separate, like if you push away from each other. In elastic collisions, no heat is generated. Really, they just bounce off each other. And energy is conserved. Energy just gets pushed from one object to another one, and we'll talk more about that later in a later unit. And in elastic collisions, they stick together. Heat is generated, and energy is lost because if you make contact, you release energy when you hit something. Like I said, we'll talk about that more later. All right, so we're going to talk about an inelastic collision first. Inelastic collision, where they hit and stick together. Okay. So a 1,875 kilogram car is going 23 meters per second when it hits another car going in the same direction on the ice. So it like skids and slows down a little bit. The two cars stick together, creating an inelastic collision. How do the two cars move together immediately after the collision? So they hit and stick together. So the momentum before the collision and the momentum after the collision are going to be the same due to the law of conservation of momentum. Okay, so here's what happens. One car hits the other one and they keep moving forward. Okay, if we draw a vector diagram, the momentum of one and the momentum of the other one is actually going to equal our total momentum afterwards. Okay. All right, so what do we know? We know the mass of each car, and we know the velocity of each car, starting velocity of each car. What we're going to figure out is what their final velocity is after the collision. So we're going to look at their final velocity together. Remember, they're traveling together, so they're both going to have the same final velocity because they're moving together. Okay, so we know the momentum before and after needs to be the same. So the momentum of both cars needs to be the same. So the mass times velocity of each car at the beginning, the mass of the car times its initial velocity plus the mass of the other car plus its initial velocity needs to equal the mass of one car and its final velocity plus the mass of the other car and its final velocity. So we're going to solve for VF. VF is equal, so that we're going to solve for VF. So because VF is equal, we can write for an inelastic collision, we can write this variation of the law of conservation of momentum. The left side remains consistent. The right side is just the sum of the masses plus the final velocity because the masses are sticking together. Okay. If you rearrange the equation to solve for VF, you get the left side divided by the sum of the two on the right. Okay, so we're going to put in our numbers, and we get the final speed of after the collision of 21 meters per second. So if you think about it, the smaller one is going faster, and the little one, the faster one, the faster one is slowing down, and they kind of meet in the middle. Okay. So velocity is measured in meters per second, and it's going in the direction of the faster vehicle, the one with the more momentum. So the one with the more momentum kind of guides which way the objects are going to go after the collision. All right. Now, let's say we have two things that are sticking together. Okay. Nope. The momentum of a baseball changes when the external force of the bat is exerted on it. So it's not an isolated system. The two colliding balls that hit, yeah, they can be an isolated system. But we're going to look at this situation. Okay, so we have two kids standing on rollerblades. They both start from rest. And one pushes the other one. And the boy's final velocity is 5 meters per second. So they start together and they push. And she's going to go one way. The boy's going to go the other way. Due to Newton's third law of motion, there's an equal and opposite force acting on it. Okay, so we're going to figure out the final velocity of the girl if we know the boy's velocity is 5 meters per second. So both skaters are moving. Okay. The law of conservation of momentum says the momentum before and the momentum afterwards are going to be the same. Okay. So we're going to go through that. This is just the math portion of this. So the momentum before and the momentum afterwards have to be equal. Before, because both of them are standing still, there is no momentum. So the sum of these has to be 0, which means they're going to go in opposite directions. Okay. So that means we know they're going to be equal the momentums are going to be equal, but just in opposite signs. So which means that the mass of the boy times the final velocity of the boy is equal to the mass of the girl times the velocity of the girl, just in different directions. And we know the mass of the boy, and we know the mass of the girl, and we know the final speed of the boy, so we can solve for the final speed of the girl. So if we take 75 times 5, gets us 375 on the left side. So 375 divided by 50 will get us the final speed of the girl, and that means that the girl is going negative 0.75, That means she's going in the opposite direction of the boy. So the lighter girl is going faster than the heavier boy in this particular case. Okay. So our last collision that we need to look at is an inelastic collision. Okay, momentum is conserved. So we're going to look at an example. Two pool balls. You shoot the 0.17 kilogram cue ball 2 meters per second at the 0.17 kilogram 8 ball that is at rest. And if the cue ball hits the 8 ball and bounces backward at a speed of 0.5 meters per second, what is the speed of the 8 ball? So we're looking for the final speed of the 8 ball. So again, back to this type of mathematical equation here. So the momentums of each and before is going to be equal to the momentums afterwards. We know the momentum of we can calculate the momentum of the cue ball because we know its mass and its initial velocity. The momentum of the 8 ball initially is 0 because it's at rest. And the cue ball, after the collision, has a mass of 0.17 kilograms and a velocity, because it's going backwards, it's negative 0.5 meters per second. And we know the mass of the 8 ball, but we don't know its final velocity. So we need to solve for final velocity. So the first thing we're going to do is do the math that's right in line with each other. So 0.17 times 2 is 0.34 kilograms times meters per second. That's our initial momentum. Okay, on the right side, 0.17 times negative 0.5 is negative 0.085 kilograms, plus we have this 0.17 kilograms times v8f, which is ultimately what we're trying to find, is this final speed. So we're going to now subtract negative 0.085 to both sides, which means we're going to add that. Okay. And then that gives us 0.425 on the left side. We need to divide that by 0.17 kilograms to get our final speed. Okay, and we do that and we get a final speed of 2.5 meters per second in the opposite direction that it was traveling. Okay. Hopefully that makes sense. Okay. So that ends the video for this. There's going to be math practice on the formative assessment. And if you have questions, please add it to the bottom of the sheet, and we will see you in class.